Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to week 2. I'm Mark Lundstrom, and we're going to continue our discussion of thermoelectric science and technology this week. Now, thermoelectricity is sometimes thought of as a topic that involves some complicated physics and some mathematics that gets a little bit involved. As you learned in week 1, the underlying physical concepts are really quite easy to appreciate. My goal in this week is to translate those physical concepts into the mathematical relations and formulas that we're going to use to analyze real devices and eventually real thermoelectric systems. So this is just a short introduction, kind of a roadmap to what's in store in week 2. And I just will dive into things here, and I'll give you just a quick overview of what's in store. So the basic experiment that we're going to be looking at is this. We have a resistor. At first it'll be a long resistor, many mean-free paths long, so electrons undergo a random walk as they go from one end of the resistor to the other. It's a large resistor, three-dimensional structure with a large cross-sectional area A. Later on we'll look at nanostructures and quantum wires, but we'll be starting with these traditional bulk thermoelectrics. The experiment then consists of doing this. We first force an electric current through this resistor. We impose a temperature difference or a temperature gradient across the resistor. We measure the voltage that results between the two ends of the resistor, or we divide by the length and convert that to an electric field. Now we also measure the heat current that flows. And there are two components to that heat current. The electrons themselves carry some heat as they go from one end to the other. And the lattice vibrations, or phonons, also carry heat, and we'll discuss both of those. So our goal is to be able to analyze and understand experiments like this and to build devices that exploit effects like this. Now the basic equations, as Professor Dada introduced, that describe this physics look like this for bulk thermoelectrics. The electric field that we measure is related to the current that we force and the temperature gradient that we impose. The heat current that we measure is also related to the current that we force and the temperature gradient that we impose. And the lattice heat flow is related to the temperature gradient. And all of the parameters in these equations have been introduced by Professor Dada. Our goal is to relate these parameters to the underlying physical properties of the material and learn how to optimize their performance for applications. Now I'll point out that these equations are coupled. There's an equation for the electric field that also depends on the temperature gradient. And there's an equation for the heat flow, which depends as expected on the temperature gradient, but also on the electric field. So we call these the coupled current equations. And then there's another equation for the lattice. Now I'll just mention one thing before we start this week, and we won't come back to it again, but what we really should be doing is not talking about the electric field that we measure, but talking about the difference in electrochemical potentials, or the voltage between the two terminals. Frequently, that's just the electric field. But if there are concentration gradients, it might be a little different. We're going to just assume that it's the electric field for these lectures. If it isn't, we would simply replace the electric field by the gradient of the electrochemical potential, or what device people call the quasi-Fermi level. Now, if you look at these expressions, they can look a bit intimidating. Here's one way to write these transport coefficients. They're complicated integrals that involve a kernel function here that's known as the transport distribution. If you look at this equation, it's not quite clear physically how to interpret this equation. Now our goal is to convince ourselves that these equations are really quite simple, easy to derive, and easy to understand, and easy to use in real applications. The approach that we're going to take to this problem is not a traditional approach. It's the bottom-up approach that Professor Dada introduced in week 1. So we're going to begin by thinking about a small nano device, and we'll see that this approach applies to large devices as well, and allows us to go from nanoscale to macroscale within one formulation. This is the formulation that Professor Dada discussed and introduced. It relates the current flow to the difference in Fermi levels between the two contacts in terms of a conductance function G. And we're going to rewrite this equation in an equivalent form. Current will be proportional to some fundamental constants, a quantity known as transmission that we'll discuss, a quantity known as the number of channels, which Professor Dada also discussed briefly, and then F1 minus F2. And we'll find that starting with this equation, we can derive the basic relations that we're going to need. We'll end up with the same equations that you get traditionally, but we'll end up being able to do that much more easily and with much more physical transparency. For one thing, we'll find that this complicated quantity called the transport distribution has a simple physical interpretation. It's just proportional to the number of channels times the mean free path. Now, we'll also find that we can rewrite those complicated equations in some very intuitive ways. We'll find that the conductance is a set of constants known as the quantum of conductance times the number of channels that are occupied times the average mean free path. The Seebeck coefficient S is related to the Peltier coefficient by a fundamental relation that Professor Dada discussed, and the Peltier coefficient is simply related to the average energy at which the current flows with respect to the Fermi level. And we'll find that the electronic thermal conductivity is proportional to the electronic charge conductivity. And we'll find that we can write the lattice thermal conductivity in a completely analogous way, a set of constants that's known as the quantum of thermal conductance. For very small structures, we can see quantized electrical conductance and quantized thermal conductance. And then just as for electrons, it's the number of channels that the phonons flow in, and just as for electrons, it's the average mean free path of the phonons. Okay. Now, this week we won't have a lot to say about devices. Really, the goal is to set the stage so that we can analyze devices like this thermoelectric power generator. But we will talk about a very simple analysis just to point out that device performance is closely tied to a figure of merit Z times temperature T, which is dimensionless. And this figure of merit is key in selecting materials and structures that have optimum performance and simply depends on the transport coefficients that we'll be getting comfortable with this week. So we'll spend some time getting familiar with that figure of merit and what it depends on. Now, I'll point out that the fundamentals that Professor Dada discussed are all discussed at much more length in his recent book. The topics that I'm going to be discussing this week are all discussed in chapters 4, 5, and 9 of a recent publication, a set of lecture notes that I've published. And I'll point out that if you would like either of these, they're actually relatively low-cost paperback to begin with, but you can get a 25% discount on either one of them if you visit the nanoHUB-U website. So finally, I just want to give you a step-by-step description of what we're going to be doing in each of the lectures. So the next lecture is actually lecture 1, and we will use this bottom-up formulation to derive the transport coefficients, and we'll show how we get those. We'll spend lecture 2 looking more closely at those transport coefficients and developing some physical intuition into what they're all about. Lecture 3 will briefly look at devices, introduce the figure of merit, and discuss the various material trade-offs that are involved in optimizing that figure of merit. In lecture 4, we'll look at some novel structures and materials, nanowires, thermionic devices, ballistic transport, and those kinds of things. And then in lecture 5, we'll bring the phonons in, or the lattice thermal conductivity, and we'll show that the same techniques that we use to analyze charge transport by electrons can be used to analyze thermal transport by phonons. Now, we're also including 2 bonus lectures, which are not a formal part of the course. The exam won't cover them, but for those of you that are interested, there's lecture number 6, which derives the same transport coefficients, but does it in the traditional way. So if you're already familiar with that way, you can see the relation between the 2 approaches. You'll see it's a little more mathematical, but you'll be able to see the connection and how we get to end up with the same answers. And then finally, the last bonus lecture, some of you are going to be interested in looking at novel materials for which their band structure is complicated and is only known by a full electronic or phonon dispersion. And we'll talk about how one applies these ideas in a more first principles sense. If you have the ability to compute first principles band structures or dispersions, we'll show you how you can then extract the number of modes and do all of the analysis that we'll be talking about in the first part of the course using simpler models. So welcome to week 2, and I look forward to working through this week with you. I hope you'll send your questions and comments to the forum, and I'm looking forward to a good discussion. Thank you.